Hey guys, welcome to video 67. Today's topic is the phase splitter, otherwise known as a cathodyne, and it's more or less a combination of a common cathode amplifier and a cathode follower in one amplifier. And the purpose of the phase splitter is to produce two output signals that are the same amplitude but 180 degrees out of phase with each other, as we can see here from these little blue sine waves I've put in the schematic. All right, if we have a sine wave coming in on RL1, VO1 is going to be an inverted version because that's the common cathode side of the circuit. And down here, VO2 is going to be a non-inverted replica of the input because this is a cathode follower. Now, we know the gain of the cathode follower is always less than 1, but it's possible for the gain of the common cathode amplifier to have a gain magnitude greater than 1. But that's not going to happen here, and the reason is because usually RL1 is equal to RL2, and RP is going to be very close to the sum of RK1 and RK2. So we're going to see about the same effective small signal resistance in the plate side that we do in the cathode side of the circuit. And remember, we're assuming R sub G is a very large value that we can ignore here as well. Now, to get a better idea what's going on, let's come on over to the AC equivalent and look at the voltage gain equations we've got. For the cathode follower, the gain is equal to Gm times R prime K over 1 plus Gm times R prime K, where R prime K is just the small signal resistance looking out the cathode of the tube. And on the plate side of the circuit, the voltage gain is negative Gm times R prime P over 1 plus Gm times R prime K. And if we have equal value AC resistances in the plate and cathode, that is R prime P equals R prime K, then we've got the same gain magnitude on both outputs. The only difference is the negative sign, which gives us the 180 degree phase relationship that we're after. And a lot of times the gain will work out to be pretty close to plus or minus 1, so we can use that approximation, and it's not going to cause any problems. And also, because of the symmetry of the circuit, that is the same resistance in the plate as in the cathode side, we can disregard the effect of little rp, the dynamic plate resistance, on the gain equations here without losing much accuracy, and it simplifies things a little bit, so that's what we're going to do here. Then finally, the input resistance again is going to be approximately equal to Rg times 1 over 1 minus the gain at the cathode follower side of the circuit, which makes R prime G, the effective grid resistance, very, very large. Now, when I'm taking the output of the cathode follower directly from the cathode, I'm going to call that version 1 of the circuit. And if you watched the previous video, you might remember that instead of taking the output from the cathode, we can come out from the junction of RK1 and RK2, and I'm going to call that version 2 of the circuit, and we're going to look at that next. Okay, so on the left-hand side of the page, we've got our modified circuit, and then on the right-hand side, we've got the AC equivalent, which is identical to the AC equivalent for version 1. The only difference is the way we're defining R prime K. In this case, it's going to be larger than it would be for version 1, and of course, that's going to reflect through the voltage gain equations. And also, we've got a voltage divider formed with RK1 and RK2. That is accounted for by this extra factor in our AV2 equation. But regardless of all these changes, most of the time the gain is still going to be pretty close to plus or minus 1, so we can use that approximation a lot of times with no problem. And the best thing to do at this point, I think, is just to go ahead and do a design example and tie all this stuff together. We're going to be using version 1, so let's go take a look at that. All right, here's the circuit we're going to be using. It's a 12AX7 We're going to set up a Q point with IPQ of 0.5 milliamps and VPKQ of 125 volts. So now let's start by locating the Q point over here on our plate curve graph, and if we go to 125 volts and 0.5 milliamps, that puts our Q point right here. And estimating the grid to cathode voltage, let's see, we're about halfway in between -1 and -1.5 volts. So let's just call this -1.25 volts. So VGK is approximately -1.25 volts, and I'll fill that drop in here across RK1. That would be positive 1.25 volts. And now we can determine the value of RK1 using Ohm's law. That is, RK1 equals the drop on RK1, 1.25 volts, divided by the current through, which is IPQ, 0.5 milliamps. And that works out to be 2.5 k ohms, which is not a standard value. I mean, if you had one laying around, you could use this, but I'm just going to go with 2.7 k. That's the closest standard value I've got handy, and that'll give me a little bit less plate current, but that's not a problem. So let's just fill that in over here, 2.7 k ohms. Now, at this point, there are a couple different ways we could approach the rest of the design, but the goal we're after here is to drop about half of the supply across the tube from plate to cathode, and then we're going to split the remaining 50% of the power supply between the top, that is the plate resistor, and the bottom, RK1 and RK2. So we've got 125 volts left over, split evenly. That would be 62.5 volts dropped up here, and 62.5 drop total down here. But let's just round this off and call it 62 volts. And likewise down here, this would be 62.5 minus 1.25. Let's just call this 62 volts as well. Then both resistors have the same value. That is, RK2 equals RP, which equals 62 volts divided by IPQ, 0.5 milliamps, and that works out to be about 124 k ohms right on the button, actually. Now, the closest standard value is 120 k, and that'll work just fine. So let's just go ahead and assign that value here, 120 k, 120 k. And the next thing we're going to do is construct the DC load line. Our first endpoint is really easy. VPK cutoff is just VPP, 250 volts, so let's mark that endpoint. And because our Q point is in the center of the load line, we really don't have to do any calculations to speak of. We know that our plate saturation current is twice IPQ, that's 1 milliamp. And we can get something very close to that if we use the equation IP sat equals VPP over RP plus RK1 plus RK2. It'll be a little bit different because we rounded these resistors to standard values, but it'll be very close to 1 milliamp. So let's fill in our DC load line, and here we go. All right, I took the last nanosecond or so and cleaned out my workspace here. And the next thing I want to do is determine the AC load line. So let's start by determining the effective AC resistance looking out the plate. And we'll call that R prime L1, which is equal to RP in parallel with RL1. That's 120K in parallel with 220K, and that's 77.6 k ohms. The next thing we need to do is find the effective AC resistance looking out the cathode, and ignoring R sub G because it's so large, that's going to be R prime K equals the quantity RK1 plus RK2 in parallel with RL2. So we've got 122.7K in parallel with 220K, and that gives us 78.8 K ohms. Now, ideally, R prime L1 would be exactly equal to R prime K, but they're off a little bit, and that just means that our gains are going to be slightly different, but they're close enough. And now that we've got these two resistances determined, we can go ahead and find the endpoints for our AC load line. So we've got IP sat, which is going to equal IPQ plus VPKQ divided by the sum of our external resistances. So that's going to be R prime L1 plus R prime K, and I guess I could have called that R prime L2, but whatever, we'll just go with what we've got here. And that's 0.5 milliamps plus 125 volts divided by the sum of these two is 156.4 K ohms, and that's 0.5 milliamps plus 0.8 milliamps, which is 1.3 milliamps. So there is our AC load line saturation current. And let's now find VPK cutoff, which is VPKQ plus IPQ times the total resistance R prime L1 plus R prime K, and that is 125 volts plus 0.5 milliamps times the sum of those resistors, which was 156.4 K ohms, 125 volts plus 78.2 volts equals 203 volts. So there's the other end of our AC load line. So let's go up and change colors and find our endpoints here. 1.3 milliamps, that would be 1.123 right about here. And 203 volts, let's see, 205, it's right about here, close enough, and we'll connect these up. And there is our AC load line, goes right through the Q point as usual. And now we need to determine where the AC load line crosses the VG equals 0 curve, and that's right here. So if we drop down from there, it looks like we have a VPK minimum of about 40 volts or so. And at this point, we will use the distance from VPKQ up to the right end of our load line to determine VO max, and the distance from the Q point to VPK minimum to determine VO min. All right, so let's see what we've got here. About 203 minus 125, so we've got a 78 volt swing in the positive direction, and let's see, 125 minus 40, that's going to be negative 85 volts in the negative direction, negative 85 volts. And normally this would be the end of our large signal AC analysis, but we're going to have another effect occurring here that causes these voltages to not be our actual signal limits. All right, if we look at the circuit for a second, consider that when the input is going positive, the plate is going negative while the cathode is going positive. And once VPK hits 0, our plate can't go any lower and our cathode can't go any higher, but they're going to hit that limit at half of the normal voltage that we'd see over here. So really, our VO max value is going to equal 78 volts divided by 2, which is 39 volts, and our VO min value at the output is going to be 1/2 of this value, or about 42.5 volts negative. So what we see here is an example of how you never get something for nothing. Since we're using this amplifier to effectively create two amplifiers, one inverting and one non-inverting, the sacrifice we have to make is that the output voltage swing for each half is divided by 2. Okay, now we're ready to do our small signal AC analysis. So let me clean off the workspace here and we'll get to it. We're going to start by finding the small signal resistance in the plate side of the circuit. We'll call that R prime P, and that's going to be RP in parallel with RL1. Remember, we're disregarding the effect of little rp, the dynamic plate resistance. In this case, because of the symmetry of the circuit, little rp is not going to have much effect on our results, so we'll leave it out to make our work a little simpler. But anyway, coming back up here, rp is 120k in parallel with 220k, which is 77.6 k ohms. Now let's look down at the cathode side of the circuit, and coming out of the cathode we see we've got RK1 plus RK2 in parallel with RL2, and remember we can ignore the grid resistor because it's so large, and that gives us R prime K equals RK1 plus RK2 in parallel with RL2, which is 122.7k in parallel with 220k, and that works out to be 78.8 k ohms. All right, now we can find our voltage gain. Let's start with the inverting side of the circuit. We'll call that AV1, and that's equal to negative GM times R prime P divided by 1 plus GM times R prime K, and plugging the numbers in here using a transconductance of 1.25 millimos, we end up with negative 97 divided by 99.5, which is a voltage gain of negative 0.97. And our non-inverting side gain is going to be AV2, which is GM times R prime K over 1 plus GM times R prime K, which gives us 98.5 divided by 99.5, which is a voltage gain of about 0.99. So we do have a little bit more gain down here on our non-inverting side than the inverting side, and we expected that because of the inequality between the effective resistances in the plate and cathode sides of the circuit. Now, this was a lot to keep track of, a lot of calculations and new formulas thrown at you. So, of course, I summarized it all, and let's go on over and look at that. And you can use this as a reference to work through the problem again if you want to, or to work through the homework assignment problem that I'll be presenting here in a little bit. But I think you can say that we're justified in assuming that the voltage gain of this thing is approximately plus or minus 1. So I'm sure you guys know by now that I'm going to give you the results of constructing the circuit and making some measurements on it, because, I mean, what good is all this painful theory if it doesn't actually work? So here's the circuit, and we've got a little bit more plate current than predicted, 0.52 mils versus 0.5, and our VPK value also came out a little bit higher as well. And I suspect what happened was my power supply was a little bit on the high side this time. I think it was closer to 255 volts or so, and that threw these off a little bit. But if we come over and look at the voltage gain, those values came out really close to the theoretical values. And over here on the scope trace, the blue waveform is my input. That's 10 volts peak to peak. The yellow trace is VO1, the inverting output. It's 9.456 volts peak to peak. So the gain is about negative 0.95. And if we come over, here's the scope trace for the non-inverting output, and you can see that when they're both on the same voltage scale, we can barely see some of the input voltage peaking out here on the top and bottom, and our gain came out to be about 0.98 versus a theoretical value of 0.99. Now, just for the heck of it, I moved my output down to the junction between RK1 and RK2, and as expected, that did reduce the non-inverting gain a bit. It went down to 0.94. In theory, it should be 0.96, and I'm going to leave that calculation to you guys. But here is the scope trace, and now you can see that the input is a little bit larger than the output, much easier to see than the previous example. And something else I did just for fun was connected channel 1 to VO1 and channel 2 to VO2, and I summed together the two waveforms to produce this sum over here in green. And if these were exactly the same amplitude and 180 degrees out of phase, this would be a flat line. We get nothing out. But you can see we do have some residual signal due to the difference in the gain of the two halves of the circuit. And also there's some high frequency noise we can see over here. And I'm not sure what that's from. I think it's from my Wi-Fi. My scope and things aren't too far from the computer, so there's going to be a little bit of RF noise on things when we do these measurements. But anyway, I thought that was kind of cool, and it's something you can do with most modern oscilloscopes these days. Now, before we go on to the homework problem, I want to summarize all the equations for you guys, just to give you something a little bit nicer to work with, because I love you so much. Here it is. It's suitable for framing and would also make a wonderful Christmas gift. Now let's go on over and take a look at the homework problem I have for you guys. We're going to use a 12AU7 250 volt power supply again. We'll set it up for 5 milliamps plate current, 125 volts plate to cathode. And here's all the data you need to get this thing done. And I will see you guys next time around.